Nigel, thank you for the invitation. I'm really pleased to be a part of this. It's a privilege. Nigel and I are in almost exactly the same birth cohort. And as I look at his CV and his extensive publications and his accomplishments, it's easy for me to be a bit depressed. But I console myself with the fact that he actually had 11-day head start on me. So there are two things I really appreciate and benefit about Nigel. And one of them is his steadfast eye on the public health consequences. For many epidemiologists, it's easy for us to go down rabbit holes, and Nigel will always be there to remind us of asking the question of, is it going to matter? And the second thing I admire about Nigel and have envied is his ability to do administrative tasks, sometimes quite heavy tasks, and not lose his spark of creativity. That spark that keeps his papers fresh and interesting. Good trick. And we should all somehow manage to do that better. So thinking of interesting results, I want to share some work that we've recently done that surprised me and my colleagues and may surprise you too. And I hope if you have some comments about it later, I can benefit from that. So I want to talk about SGA, which for this audience, I hope doesn't need translation, small for gestational age. It is typically the smallest 10% of fetuses or babies at each gestational week. And it's used as a research endpoint in thousands of papers in all kinds of disciplines. So what does it mean? These data show neonatal mortality risk by the percentile of birth weight collated across all the gestational age strata. And what you can see is when we get down to the lowest percents, the smallest percents of birth weight, and the y-axis is on a log scale, that the risk gets extremely high. And so it raises the question of what is wrong with these babies. We know they're not preterm because we've controlled for gestational age. So what is there about being small that is so dangerous? It's a 20-fold higher risk from the most protected to the most at risk. And the answer we usually give to that high risk is fetal growth restriction, or FGA. This is a syndrome that's described as pathological restriction of growth in infants, reflecting inability of the fetus to get enough nutrition either from the mother or through the placenta. It can be caused by poor nutrition or all these things that can go wrong with the placenta in transmitting that nutrition and oxygen. So the problem with studying fetal growth restriction is we don't have a clear clinical definition of it. That's a problem. So historically, it was defined as SGA. And it continues to be, SGA continues to be studied in many circles as fetal growth restriction. But the underlying problem is that fetal growth restriction is not the same as SGA. Overlapping, surely, but not the same. Babies who are constitutionally small can be entirely healthy and small. And some fetal growth restricted infants can be larger than the smallest 10%. You can imagine a baby destined to be 9 pounds and comes out at 6 pounds, has undergone extreme growth restriction, and yet is not small by conventional definition. But this doesn't keep us from falling back on the equivalence of SGA and FGR. Epidemiologists for sure study SGA and regard it as a clinical outcome, an expression of fetal growth restriction. And the clinicians likewise, although everybody pays lip service to the fact these are not equivalent, if you look at the latest up-to-date review of an authoritative clinical website, it says this: moderate FGR defined as SGA third to the 10th percentile, severe FGR is defined as less than the third percentile. Somehow we can't escape this. So some clinicians have tried to refine the relationship between fetal growth restriction and SGA with this purely imaginary figure, but it conveys the general idea that with fetal growth restriction in the orange and healthy babies in the gray, that as the percentile gets smaller on the x-axis, the likelihood that it's an FGA baby increases. And in this imaginary diagram, they are assuming that the FGA babies reach 100% at somewhere down around the third percentile. So can we be more objective about this? Can we find what would be the optimum cut point of SGA to identify babies who are truly fetal growth restricted? There are lots of definitions. If you look at the literature, 10% is most common, but fifth percentile is another one, 2.5 or 2 standard deviations is one we see increasingly often, with the notion that the more extreme the percentile, the better we're defining as FGA. So I wanted to ask what I thought was going to be a very simple question, which is to say, what percentile actually does the best at predicting the high-risk group? And the tool that's at our hand, of course, is ROC analysis. ROC curves are made for this question. They're the tool that we use clinically to evaluate a continuous predictor, like SGA, and a dichotomous outcome. And in this case, I'm going to use neonatal mortality. So this seemed like a slam dunk. And if I identify that the 4th percentile of SGA was going to be the optimum cutoff, I could write a paper that would get lots of citations. So, and in reviewing the literature, nobody had ever done this. So good, we'll proceed. So you all know this stuff, but let me just remind you that the receiver operating curves plot sensitivity versus 1 minus specificity. And we plot those values at each point on our continuous variable. And it gives us a curve that we can then interpret. And it also gives us something called the Yoden point, which I'll return to in a second. So the way we interpret these curves in general is that if it's a straight line from the bottom left to the upper right, that means our predictor is useless. You can flip a coin and do just as well. And the more curved that receiver operating curve is, the better a predictor it is. And this is kind of the standard classification of areas under the curve. Looks a lot like how we grade students. And then each curve has a point that is closest to that upper left-hand corner, and that is called the Yoden cut point, and that maximizes the sensitivity plus specificity, would provide the optimum SGA cut point. So super. Let's do it. I took US data from Vital Statistics for a recent 5-year period. And this is what I found. The area under the curve was 60%. That's called borderline failure. I was surprised. And I thought, could there be something about the vital statistics data that is sabotaging me here? So I went to my Norwegian colleagues and I asked them from data from their medical birth registry, which is presumably more carefully collected and less subject to all the various state variation that goes on in the US. And you can see that we got exactly, and I mean almost exactly, the same result. So one consequence of this very poor area under the curve is that there's no optimum cut point. There's no cut point for SGA that we can recommend that optimally separates the at-risk babies from the not at risk. So my next thought was, maybe there's something about neonatal mortality that's not a good outcome here. It's very rare, right? So let me just look at another continuous variable that we know is associated with neonatal mortality and see if it's just as bad. And the thing we picked was gestational age. So we looked at each level of gestational age at birth to see how well it predicts neonatal mortality. And this is what we found. Area under the curve was 85%. That's pretty good. In Norway, we replicated it exactly the same. And really the most interesting part of this was the Yoden cut point. What do you imagine the gestational age is that most accurately predicts what a high-risk baby is going to be? It turns out that it's less than 37 weeks. And that floored me because this is a totally objective way of making that determination. And so I went into the clinical literature to try and figure out where less than 37 weeks came from. And nobody knows. It's been used for at least 100 years. But somehow the accumulated clinical wisdom of setting it at this gestational week turned out to be the very best way to define preterm babies. So I'm left with the conclusion that SGA is really a crappy measure to predict risk. And clinicians are coming around to the same idea too. There's a recent paper that looked at other aspects of SGA research. There's lots of things to complain about in this using SGA, and they said, we're at an impasse. We got to do something. So the reason we're at an impasse is because SGA is just functionally useless. The clinical challenge is to find a criterion or more for fetal growth restriction that's independent of baby size. And for that problem, I'm going to turn to the rest of the people in this room. That's outside my bailiwick. Thank you very much.